That car can do 140 miles an hour. It's also got squeaky brakes. Now, brake squeal isn't disastrous, nor does it mean that there's something wrong. It's simply annoying, very annoying and irritating. In fact, it's been a problem since brakes were invented. People have been trying to cure it for that long as well, but they haven't managed to solve it yet. Why not? What exactly has been done about the problem? Where in particular does the maths come in, the sort of maths you've seen in units 10 and 11? We hope by tracing the history of this investigation, we can show you how that maths fits in. To start off with, I'll have a look at what the brakes themselves look like. Right, I'm in a garage belonging to the Motor Industry Research Association, or MIRA for short, and they've stripped down a couple of brake assemblies for us to look at. First of all, let's look at the discs. This is the disc. Surrounding it are the calipers. Inside the calipers, you can see in the centre bit of the disc, and on either side of that, the brake pads. I can take one of these out to show you. When the brake pedal is depressed, pistons inside this caliper ram the brake pads against the disc, and it's when the pads and disc are in contact that sometimes you get squeal. So much for disc brakes. Most commercial vehicles have drums, so let's look at some of those. Instead of pads, we've got brake shoes, which, when you depress the brake pedal, move outwards and rub against the inside of this enormous drum. It's this size to get the braking required and also to dissipate the heat generated. Now, they've done a lot of work on both disc and drum brake squeal at MIRA. One of the people who's done the work is Mr. Fosbury, the Assistant Director. How seriously do manufacturers take the problem of brake squeal?
Well, in the days that I was involved with it, it was regarded very seriously, particularly by the bus people. I mean, I've known cases where the police have actually sent buses off the road because of the noise made by the brakes. So this is a pretty serious problem to have your bus taken off. This was back in 1955. And we started off with the assumption at that time it was generally thought that brake squeal was due to a frictionally induced vibration, either from a static coefficient of friction higher than the dynamic coefficient of friction, or a falling coefficient of friction with increasing speed. So first of all, we looked to see whether the torque characteristics of a squealing brake were different from the torque characteristics of a non-squealing brake. And we did in fact find that this was so for very slow speeds. And having got to that point, it looks then as if it was the lining characteristic which was the chief factor. Now, lining characteristics are difficult to control. This becomes, quite apart from anything else, it's a chemist's job and not an engineer's job. So we, in terms of looking for a solution, went to look for a solution in terms of damping the vibration.
What sort of thing did you turn up with?
Well, we first of all looked at the drum system from the point of view of where it was vibrating. And one of the things that we found was that for the normal squeal that you hear on the road, the drum vibrates more like a bell. And we then found a particular form of damper. And here's your drum. As you see, it is more or less like a bell. So the way to damp this is to put a piece of friction material there against one of the ribs, put a backing plate behind it. We then bolt it down, and then when the drum tries to squeal, the relative motion between the drum and the friction material damps it out. And then depending on the intensity of the squeal, you can have, say, 8 or 6 of these pads around the rib of the drum.
Yeah. And well, that's pretty complicated, but let's get one thing straight before we go on. At the time of your investigation, it was generally accepted, was it, that variation in friction was the main cause of the squeal?
Yes, this was the generally accepted theory, and I think that what we had found out didn't contradict it. It didn't really prove it either.
Well, what is this friction variation that Mr. Fosbury was talking about, and why is it believed to be a source of vibrations? Well, there's a section on self-induced vibrations in Unit 11, and in that section you'll find a diagram of this model. I'm going to set this belt moving with a constant speed along here, and I want you to watch what happens to this mat as I put it on. I want you to note that the belt is moving in this direction, so as the mass moves with it, its relative velocity is less than when it's moving against it. So if the friction between the two is varying with velocity, then obviously the frictional force is going to vary. And this is in fact what gave rise to that oscillation which gradually built up with time. Okay, so how do we mathematically model this varying frictional force? Well, we have the frictional force falling off with velocity like this. And if the range of relative velocities is not too great, then we can model it with a straight line, the slope of the straight line being minus a2. Obviously, if we're working on a different part of the curve, then we can use a straight line again for this frictional force, but of course the value of minus a2 will be less. Now, in the unit, we've shown you how this model for the frictional force leads to an equation of motion of this form, and we're going to concentrate on this term here, the damping term, because it's this that incorporates the varying frictional force. Now, if the natural damping C is greater than A2, then we get the usual situation of a positive damping, and these are the sort of equations the sort of solutions that we get. The interesting new situation, though, is when A2 is greater than C, and then that gives us a term which is overall negative, and we get a new type of solution with the oscillation building up with time. So you see, this mathematical model can therefore account for the variation, can account for the vibrations that we got with that moving belt, and so it was natural to assume that friction variation was similarly the root cause of the brake squeal. Well, when disc brakes came in, as opposed to drum brakes, it was found that they squealed too, so the work at Myra had to start all over again to find out just exactly what was vibrating and in what way. So Mr. Fosbury went on to show Keith the sort of experimental rig that they used.
This is the current rig we're using. We have a caliper and disc driven by an electric motor, and we have accelerometers on each end of the backing plates of the friction pads, and we feed the signals from these through this box onto the oscilloscope, where we can get a measure of the way in which the pads vibrate this way and the way in which they twist. We've also got a vibration pickup here for measuring the vibration of the disc, so that you can identify the nodes and antinodes of vibration of the disc. These all switched on from over here.
Well, that all looks pretty complicated, but still it's simpler than drum brakes. Did you try any mathematical modelling?
Well, we did think about mathematical modelling of the disc system, and I took this to our resident mathematician at the time, but I'm afraid he just threw his hands in the air and said it wasn't on. I think largely that the computing facilities and the numerical techniques were just not available to do a system of the complexity of the disc brake.
Right, thank you, Mr. Fosbury. So let's get clear what the situation was in the early 60s. We've got the problem. It occurs on both drums and disc types of brakes. It was generally accepted that variation in friction was the cause, and no attempt had been made as yet at mathematical modelling. Now, this situation changed somewhat in 1963 with the appearance of a paper by Jarvis and Mills. This described experimental work done on a simplified version of a disc assembly. That's just a sloping cantilever rubbing against a disc, and also gave a detailed mathematical analysis of that system. We can take the story up with Dr. Jarvis himself.
Oh yes, at this time I noticed from my analysis that it was possible for an instability to arise just because of the coupling between the two members. So we devised a rig where each component by itself could be predicted, and then we could concentrate our attention on their behaviour together. The cantilever is subject to two forces. It is pressed on by the normal force from the disc and the frictional force from the disc. And if you increase one, you increase the other. If the force increases, that would tend to push the cantilever away, but the frictional force would tend to pull it down, and the effect of friction is the greatest. So when you push, it comes towards you. So seen from the disc, the cantilever would appear to have negative mass, negative damping, and a negative spring rate.
So this leads to self-excited oscillation?
Yes, if the negative damping of the cantilever exceeds the damping of the disc, then the whole system would be unstable. It was useful because it gave an explanation of how the squeal arose, and it showed the importance of the damping of the two components and the way in which they're coupled.
So Dr. Jarvis provided a completely different explanation of brake squeal. He was the first person actually to show that it was nothing to do with the variation of friction at all, but it was somehow associated with the way in which the disc and the pad are constrained to move together. So, well, let's take a closer look at this approach. We've constructed here an experimental setup rather similar to Dr. Jarvis's. This is a disc from actually from a real disc brake assembly. Here we've got the cantilever, and it's tipped with brake pad material, and I can vary the angle. Well, okay, let's see if I can get it to squeal. Oh, very easily, in fact. Now, of course, the reason why Jarvis and Mills used this very simple setup was that it was susceptible to mathematical modeling. And what I would like to do now is, in fact, to take you through a simplified form of Jarvis's mathematics. We'll begin by noticing that the disc can vibrate from side to side like this, and the cantilever will waggle up and down something like this. Now here you can see the type of movement more clearly when we link these two together. Okay, well, let's concentrate our attention on just a bit of the disc and the tip of the cantilever. The bit of the disc you see is going to move along x1 and the tip of the cantilever along x2. And both these parts are going to be acted upon by the same forces. There's going to be a reaction force R and a frictional force mu R. And with these forces we can then go ahead and get the equations of motion for the two parts of the system. Okay, well, let's first of all concentrate on the part of the disc. It's moving along x1, and the only force in that direction is R, and that's how we get this simple equation of motion here. M1, C1 and K1 are just simply constants associated with the properties of the disc. Then, with the tip of the cantilever moving along x2, you'll notice that this time both of the forces have components along that direction. And so if this angle here is alpha, that's how we get this expression for the equation of motion for the tip of the cantilever. M2, C2 and K2 are now simply associated with properties of the cantilever. So there it is then, two equations of motion. But there are three quantities here which vary with time. There are the two displacements, x1 and x2, but also R, the reaction. This is also varying with time. And so we need a third equation. And this is where we take into account the fact that the tip of the cantilever and the disc are moving together. So, for example, if I move this over to here, you'll see if the disc moves a distance x1 then that automatically fixes what x2 has to be. And that's expressed in this third equation, and this is the important equation which expresses the coupling between the two systems. Right, well, you'll find those equations in the TV commentary, and after the program I want you to play around with them, get rid of the x2 and r, and you should then end up with this expression for x1, the equation of motion for the disk. Once again, let's concentrate on the damping term. The c's are the damping coefficients, m's are the effective masses, and the new quantity there, f, is simply defined in this way. Depends on the angle alpha and the coefficient of friction mu, which, remember, in this particular model we're taking to be a constant. Now, the interesting thing about that expression is that it can go negative. If, for example, the denominator is positive and C2 is greater than C1F, then clearly the whole thing is overall negative, and that will therefore give rise to a self-excited oscillation and hence to brake squeal. Now, what I would like to do is to alter our system so as to alter those constants to different values and see what happens. So let's go back to that experimental rig and see what we can do. Remember, I said that M2 and C2 depended upon the characteristics of the cantilever. Well, I can very easily change the characteristics of the cantilever just by altering its length. And so that will effectively alter the constants in the mathematical model. So what I'll do is progressively lengthen the cantilever, and, well, you just listen to the results. Oh, that's interesting. Can't get a squeal that time, but let's press on. Carry on lengthening it. Squeal's coming back. Oh. That's enough of that. Well, obviously, the interesting thing about that was that, in fact, there was one length of that cantilever for which there was no squeal at all. And this means that in the corresponding mathematical model, there must exist a combination of coefficients such that the overall damping is positive. Now, of course, this raises a very interesting possibility for the proper brake assembly. For that assembly, we might also find a combination of constants such that there would be no squeal at all. Now, of course, with a proper assembly, there are many components. Each will have its own equation of motion, and so the overall equation of the vibration of the disc is going to be pretty complicated. But nevertheless, the hunt is now on for a design which will produce no squeal at all. And, well, this is where we bring our story up to date. Keith finally talked to Mr. Michael North at Myra about his work on brake squeal.
Well, my approach has been theoretical, like Dr. Jarvis's, with the difference that I have tried to represent as closely as possible an actual brake system consisting of a caliper, disc and pads.
And how do you set about doing this model? Do you use anything of the simplified work?
Yes, I use the point brought out by Dr. Jarvis that a disc can hold two independent modes in space. This means that if you consider the periphery of a disc unwrapped to form an x-axis running from minus 180 to 0 to plus 180 degrees, and a y-axis which shows the amplitude of vibration at the edge of the disc, then the disc can hold a sine mode, which can be drawn like that, and a cosine mode, like that, and that any general vibration in disc mode order 1 consists of the sum of these two components.
So what does that tell you about that bit of the disc?
Well, this allows you to model the portion of the disc in the vicinity of the pads and the caliper where it will interact with the pads and the caliper. The pads are centered on theta equals 0. So this is the pad region. And the sine mode can be modeled by a portion of the disk, or a beam, which rotates like that. And the cosine mode can be modeled by a portion of the disk which has a translational movement like this.
Right, so that's a model for the disk, but what do you do about the rest of the system?
Well, having represented the disk in the immediate vicinity of the caliper, which is the region here we're interested in, you can then add the other components, the pads and the caliper, into the system. So the disk is represented by a beam with the 2 degrees of freedom we just mentioned. And this has a stiffness and a damping to some reference point, say the stub axle. Then connected to this are pad 1, which is connected by stiffness and damping, and is a beam with the same 2 degrees of freedom. Likewise, pad 2 is connected to the disk by stiffness and damping, and is represented by a beam with the same 2 degrees of freedom. And finally, the caliper can be drawn in, enclosing the whole system, and connected to the pads by stiffness and damping. Into this you can draw the frictional forces, which are tangential to the disk. And if you write the equations of motion for a system like this, you should have a reasonable mathematical model of something that looks very like the brake system we're interested in. You write the equations of motion, and since you have allocated 2 degrees of freedom to each of these 4 components, you end up with 8 second-order differential equations. And these can be combined to form one 16th order differential equation.
This is fine as a theoretical solution, but what practical use is it?
There must obviously be a program of experimental work connected with this. At this stage, we have a mathematical model which describes a squeal mechanism and correlates well with a rig and shows qualitatively how a lot of the observed facts of squeal arise. The next stage must be to use this model in conjunction with an experimental program of work to try and show how these areas of instability can be avoided by design.
So there it is. We don't know yet that it's a success story. We don't know that North's model is going to produce the goods. What we have shown is the part that mathematical modelling plays in real technology. The other parts consist of a lot of trial and error engineering and some attempt at an understanding of the physical basis of the phenomenon. The very least that mathematical modelling has done in this case is to isolate the cause of brake squeal. The most it has done is to provide the design engineer with a tool with which he can eliminate it.